let's go ahead and spend some time talking about solution formation. What do I mean by solution formation and what's causing a solution to form? You often have this happen in your everyday life. You just may not always think about it or realize it. So we'll learn a lot more about this as we go through general chemistry and what solutions will form and what won't. But we do have to have a basic understanding of it coming into reaction predicting for this course. There are different things that will combine. We're going to learn about concepts such as like dissolves like, meaning compounds that are similar like to hang out together, and they will be able to dissolve each other. If you are cooking, people often add salt to their water to make it boil faster. If you walk through a parking lot and you see the really pretty colors on the ground where there's water and it looks like really pretty colors floating on top, that's the oil floating on top of the water because oil and water don't like each other. They're not going to make a solution. So all kinds of things go into solution formation, but we need a little bit of an understanding of it in first semester so that you guys can do some calculations. So a review of some vocabulary you're going to see in this semester is the following: solution and solvent and solute. So one thing I want to make a point of is when I say mixture, a mixture is something that is made of two or more components that can vary in proportions, such as a metal alloy or sweet tea. What is a metal alloy? Metal alloy is a piece of metal that's made up of multiple metals itself, whether it be two or more individual metals. Stainless steel, for example, is a metal alloy. Stainless steel has nickel, it has iron, often has chromium, often will have molybdenum. Depending on which type of stainless steel you have, it'll have a different composition. And I have lived in Texas for a long time, but I was not born and raised here, so I have never grown into liking sweet tea, which is almost blasphemy down here, but it is a very popular thing to drink, sweet or unsweet tea here in Texas. And if it's sweetened, well, you probably are not sweetening it the exact same way as someone else. So what is a solution? A solution is a homogeneous or uniform mixture. Homogeneous means that it has the same composition throughout the entire solution. So for example, if I take a glass from my cupboard and I fill it with water, just water, if I test the water at the very top of the glass versus the water at the very bottom of the glass, it will have the exact same composition. No matter what, it's going to have the same things in it at each point within that sample. If I then add some ice cubes to my glass, it is no longer homogeneous. First, there's a temperature gradient. The water closest to the ice will be colder, but also there's ice cubes, which are in a different phase than the water itself. So a solution is defined as something that's homogeneous, meaning it's uniform, and it's a mixture. It consists of two components: your solvent and your solute. You may have multiple solutes in here, but you have at least one solute and you have a solvent. The solvent is the solution component that's present usually in the largest amount. It doesn't actually have to be the largest amount, but more often than not it will be. It will be the species that does not change phase when the solution is mixed. So sometimes you can actually dissolve something in a higher or greater concentration, but it will not change phase. So in general chemistry, this is usually going to be water. Not always, but it will usually be water. Your solute is the dissolved substances that's usually present in a smaller amount, but it will absolutely change phase. So if you have salt water, the salt is your solute, the water is your solvent. If you have sugar water, sugar is your solute, water is your solvent. So you see the trend here, water is often our solvent. Again, it doesn't have to be. The way to tell is if you have a solute and solvent, if you mix two things together and they are in different phases to start, meaning one is a gas phase, one is a liquid, one is a solid phase, and one is a liquid. Whichever one changes phase is your solute. Whichever one stays the same phase, that one is your solvent. If they're both in the same phase to start, whichever one you have more of at the start before mixing is your solvent. And here we just have some pictures that we'll discuss more on the next slide or on a couple slides, kind of showing you what different solutions can look like. We do want you to be very proactive in trying to think about what this stuff means. So if you can see this in your mind, it will actually make your life a lot easier in this class. One of the most difficult parts of chemistry, besides the learning of the foreign language part, the foreign language being chemistry, and the math problems that we do, is that it's really hard to see what's happening at the molecular level. Sketching this out or writing out diagrams could benefit you greatly as you try to determine what's actually happening. So try working on developing an imaginary picture in your mind of the atoms or molecules in a solution. How are they interacting? What are they doing? What's happening? Why are they dissolving? It will help you better understand what's happening in the solution if you can start to identify what it looks like in a solution. So when will a solute dissolve? We will get into this a lot more in second semester, near the beginning of second semester, but there are these attractive forces that are holding solutes together and holding solvents together. So we have a solute-solute interaction, we have a solvent-solvent interaction. When we dissolve something, we're creating a solute-solvent interaction. And basically what's happening is we have to make that solvent-solute interaction stronger than the individual interactions themselves. So we see here in the picture, in the bottom picture, we've got a sodium chloride ion. Sodium chloride is table salt. So if you've dissolved table salt in water, this is what you've done. And they have a solute-solute interaction. When put into water, which is what that little, the little molecule that has the red ball with the two white ends, that is a water molecule. When put into water, water also is attracted to itself. Hence, it forms water. It stays in a liquid form and it stays into solid form when we make it really cold, when we freeze it. When I put this in solution, the sodium ions are attracted to a portion of that water molecule. The chloride ions are attracted to a different portion of that water molecule. We will talk more about that later on this semester. It's this concept called polarity and electronegativity. We'll talk more about that when we start describing how these compounds are actually constructed and put together in a 3D world. Right now, what you need to understand is that there's an attractive force that's actually pulling that sodium chloride away from each other and allowing it to dissolve in the water. So if the attractions between your solute and solvent are strong enough, the solute will dissolve. So ionic compounds and molecular compounds behave differently. Ionic, we'll talk more about again in first semester, but ionic is when you've got two oppositely charged particles making a compound. Most often it is a metal and a nonmetal. It doesn't have to be. It could be two charged polyatomics as well, but it will be two oppositely charged species that are attracted to each other. When they are put into water and when they dissolve, it's actually called a dissolution. This is because they actually break apart from each other entirely. So what we see here is we're putting sodium chloride crystal, again, table salt, into water. The water molecules are going to surround this compound. And when they do it, they orient themselves. Water has a positive end and a negative end to it. The oxygen has a partial negative charge. The hydrogens have a partial positive charge. Again, we will talk about that when we talk about electronegativity and polarity. But the negative side of that water molecule surrounds the positive ion, specifically from that sodium ion that's in that crystal. When 6 waters surround that sodium ion is no longer attracted to the chlorine that it was originally coupled up with in the crystal, and it leaves the crystal. The hydrogen ions, which have a partial positive charge, hydrogen ends of water, the hydrogen side of the water has a partial positive charge to it, and that orients itself in relation to the chloride ions. When 6 water molecules with the hydrogen ends aiming towards the chloride ions surround a chloride ion, the chloride ion then lets go of that crystal and leaves with the water. This is again called a dissolution because it's completely breaking apart that crystal into their individual ions. The ions enter the solution, they're surrounded by the water molecules, and these water molecules then isolate it from other ions in solution. So we have free-moving charged particles in solution, and these are able to conduct electricity. These are known as electrolytes. Electrolytes conduct electricity. So these ionic compounds that dissolve and form ions in solution are able to conduct electricity. So dissolving of ionic compounds, we do call this a dissociation reaction. The ionic compound, which is often called a salt, dissolves in water. We represent this by writing the solid phase as a reactant. As shown here, we see NiCl2. That means nickel chloride, nickel 2 chloride. We will learn naming in first semester as well. We write this as a solid. We then write an arrow to show that that is the only reactant, and we write the two products as their individual ionic species. We don't write water anywhere. Instead, we write the little AQ after the nickel 2 plus and the Cl minus to emphasize that they are dissolved in water. AQ stands for aqueous. Aqueous means dissolved in water. So again, once dissolved, the state of the ions is aqueous or AQ to indicate the ions are dissolved in the water. We do not include water on any side of the reaction other than specifying AQ for the phases of the ions. When you do a reaction like this, you do need to make sure your charges are balanced. We'll talk more about that in first semester. Right now, we just really want you to understand why these solutions are forming. And special note here, we have chloride ions present, not chlorine gas. Be careful with your diatomics. Chlorine is one of your 7 diatomics you guys are going to learn. There's 7 elements that exist as what we call a diatomic, meaning 2 atoms conjoined for better stability, better energetically favorable reasonings. This is chloride ion, not chlorine gas that is present in here. We do not get nickel ions in chlorine. We get nickel ions in chloride ions. Just like if I dissolve sodium chloride in solution, it is sodium ions and chloride ions, not sodium metal and chlorine gas. And lastly, dissolving molecular solids. This is a dissolution-only process. What do I mean by molecular? I mean something that is consisting of just non-metal species. We'll talk about how you identify metals, nonmetals, and metalloids in first semester. You'll get to it very quickly in first semester. But molecular solids don't break apart. They just dissolve. So no ions are actually formed here. No covalent bonds are broken. Ionic compounds have ionic bonds. Covalent compounds, molecular compounds have covalent bonds. In an ionic compound, there's a complete transfer of an electron. In a covalent or molecular compound, covalent bonding is a sharing of electrons. Thus, molecular compounds are formed between non-metal species. And so what I see here when I put sucrose or sugar into water, the water still kind of surround the sucrose molecule, but it's not going to break it apart. So it's dissolved in a dissolution process only.